Greetings, fellow mathematicians. We're going to take a look at two sequences that you will be deceived into trying to apply L'Hopital's rule to them. Now, we're going to find that L'Hopital's rule really doesn't simplify the limits at all. It doesn't do anything for you. So we're going to need alternate methods, which is the goal for this video, to point out what to do if L'Hopital's rule is not helpful. So let's take a look at the first one. This is a peculiar one. Let's check first that it involves an indeterminate form. So we want to check what the numerator and denominator approach. And 2 to the n and 3 to the n, as n approaches infinity, well, they're both going to get bigger. So the numerator approaches infinity. And 4 to the n, as n approaches infinity, well, that gets bigger too. So the denominator approaches infinity. Now, in order to differentiate these are exponential functions, but they're base 2, base 3, and base 4, not base e. Exponential functions, base e, like e to the x, they differentiate very nicely. They just give you itself as the derivative. If it's any other base number, we're going to write that as base a. So in other words, if your base is any number but e, it's slightly more complicated. You get a factor of natural log of a times the exponential function a to the x. All right, so if you were to apply L'Hopital's rule here and differentiate this term, notice what that would turn into. This would differentiate 2 to the n to natural log of 2 times 2 to the n. And when we differentiate 3 to the n, we get natural log of 3 times 3 to the n. And then differentiate your denominator individually, you'll get natural log of 4 times 4 to the n. And that's actually making the term and limit look a lot more complicated. Now, it is correct to apply L'Hopital's rule, but it doesn't simplify the problem for you. It makes it worse. So L'Hopital's rule, we're going to forget about it. We're just going to try an alternate method. And a lot of times it's just rewriting this in a particular way that will make finding the limit much easier. And here what we're going to notice is we have exponents of n everywhere. And I have terms that I can divide. I can divide 4 to the n into both terms in the numerator individually. So we're just going to use a basic way to rewrite fractions, and that's the alternate method to applying L'Hopital's rule here. So if we take a look at our term a sub n, 2 to the n plus 3 to the n divided by 4 to the n, I'm just going to rewrite that 2 to the n over 4 to the n, but because the powers are equal, I can write that as 2 over 4 all to the nth power. And same thing when I do 3 to the n divided by 4 to the n. Since they're both to the nth power, I can write that as 3 over 4 to the nth power. And here we're basically done because now, as n gets bigger, the numbers inside are both less than 1. So as n goes to infinity, both these terms are going to approach 0. So what we can conclude without using L'Hopital's rule is that the limit for this example, the limit as n approaches infinity of this term, that's going to come out to 0. So your basic technique here, not L'Hopital's rule, but just rewriting the term in something that's a little easier to deal with. All right, let's go to the second example. Again, you want to check if you are able to apply L'Hopital's rule. So as n goes to infinity, square root of n is going to keep increasing. And the same thing with the denominator. So we do get an indeterminate form of type infinity over infinity. And let's go ahead and try to apply L'Hopital's rule to to this. So we're just going to calculate the derivatives of numerator and denominator individually. It might be helpful to rewrite this as n to the 1/2, and then this denominator as n plus 1 to the 1/2. That's going to make finding the derivatives a little bit easier. And now if we differentiate, I'm going to apply the power rule, but I'm going to rewrite it. The 1/2 comes down. You'll get n to the negative 1/2. I'm just going to rewrite that as that fraction. And I'm going to do the same thing here, technically applying the chain rule. Bring the 1/2 down. You'll get now a negative 1/2 power. And you can rewrite that all as this fraction. We can simplify this. We have a fraction divided by a fraction. So I can multiply by the reciprocal there. And while you can cancel the factors of 2 out, notice what this reduces to. This gives you the function square root of n plus 1 over square root of n. And that is pretty much the original term for the sequence, but just flipped. So if you were to apply L'Hopital's rule, you pretty much get the same term, just flipped. This is again going to give you an indeterminate form, infinity over infinity. Go ahead and try L'Hopital's rule again. That's just going to flip back and get you back to what you started with after 2 applications of L'Hopital's rule. So due to how square root of n or square root of x differentiates, this term is just going to keep going back and forth. L'Hopital's rule will not help you. So we're going to need an alternate method, which again is rewriting that. Now what we're going to make use of are what I call reciprocal limits. We're going to make use of limits like the following. The limit as n goes to infinity of 1 over n, that limit is 0. So we're going to try to rewrite this function, or term I should say, function of n, if I want to correct myself. We're going to try to rewrite that so that way we can have reciprocal terms in there. All right, so let's start with our term. We're not going to apply L'Hopital's rule. So we're going to take a limit as n approaches infinity of square root of n divided by square root of n plus 1. And if I want to get a reciprocal 1 over n in here, I can factor n out within that square root in the denominator. That sounds like a mouthful, but what we're going to do is factor n out within the radical, the square root. And make sure you're comfortable with this. In an earlier algebra course, you might say that 1 does not have a factor of n in it. Well, you can cheat. Check this by distributing. You can factor n out if you're willing to write that term at the end of the parentheses as 1 over n. Check by distributing. N times 1 gives you n. N times 1 over n, that does give you 1, so that's correct. And what we're going to do from here is basically take the square root of each factor, n, and 1 plus 1 over n. And now we have our reciprocal term. Again, we are not applying L'Hopital's rule. We're just algebraically rewriting the term of our sequence. The limit remains the same, approaches infinity. And now we're making use of how we rewrote that square root in the denominator. And we're basically done. Notice the square root of n's cancel out. And if I want to write down the limit that we have here, or the simplified term, here we're left with the limit as n approaches infinity of 1 divided by the square root of 1 plus 1 over n. Now we have our reciprocal. That is in the square root in the denominator. As n goes to infinity, 1 over n is going to approach 0. And notice what we're left with. The numerator remain constant as 1. We basically get 1 over square root of 1. And that all just simplifies to 1. All right, so not that complicated, but definitely tricky, especially if you're thinking that you always want to apply L'Hopital's rule. Definitely take away from these two examples that it is possible that L'Hopital's rule does not help you at all. So we went through how to get around that. In 2 simple words, you rewrite the sequence. I guess that's actually 3 words. So rewrite the sequence instead of applying L'Hopital's rule, and that does it. Hope you enjoyed the video. If you did, support the channel, like and subscribe.